his latest book, The Allure of the Multiverse, the popular science writer and physicist Paul Halpern raises a wide range of extraordinary questions about the universe. But three of them in particular, in his reckoning, lead to the multiverse. Is reality such that anything that can happen must happen? How does quantum mechanics choose the outcomes of its apparently random processes? And why is the universe habitable? The remarkably detailed account by Halpern, who is a professor of physics at St. Joseph's University and the author of 18 books, makes for a terrific and stimulating reading. Professor Halpern spoke to Mayank Chhaya Reports, explaining why we need to keep an open mind about a multitude of bizarre possibilities. Welcome to Mayank Chhaya Reports, Professor Halpern. It's a great pleasure to have you on.
Thank you. It's good to be back again.
Yeah, it's been a couple of years since we last spoke.
Yes, a few things have happened in the world since then, but
Oh, yes. Uh,
yes, but it's
Speaking
always a
of
pleasure.
which, early on in your book, you talk about the pursuit of a unified explanation of natural forces. By some coincidence, we are talking barely within a week of what is claimed to be a radical new theory, somewhat awkwardly named the post quantum theory of classical gravity, which sounds to me like postcoital depression, but levity aside, this theory is supposed to be the holy grail of physics, which consistently unifies gravity and quantum mechanics while preserving Einstein's classical concept of space-time. What do you think? I'm sure you've read reports on that.
I've seen news reports. I haven't looked at the articles yet about that theory, but I think the big problem is that general relativity is a classical theory. It's deterministic. It is something which involves a seamless fabric. It's not discrete. Quantum physics involves, in some cases, discrete quantities. It involves probabilistic calculations and processes. So it's these are very different, and nobody has able to find a way, and I'm not sure about this new theory, but up till now at least nobody's found a way to be able to unite the two. And there are many different proposals, some of them based on general relativity and then trying to extrapolate from relativity to get to quantum physics. For example, John Wheeler had this idea of superspace, in which you take many different geometries, all the possible geometries that fit into general relativity. So you have this host of solutions, all of them representing different structures. For example, a flat space-time, a space-time which is kind of the extension of a sphere, and then taking these geometries and making a quantum model out of those, in which those are all different elements, different building blocks, and you have some probabilistic mix of those that leads to our own universe through some kind of quantum process. And the opposite would be to start from quantum building blocks, look, for example, at quantum states, disregard the idea of space-time itself in the beginning, and then try to construct space-time from quantum operators.
Right.
So there are many different ideas, and I'm excited to look at this new idea, but I should caution everyone that there have been many failed unified proposals over the years. Hopefully there will be a successful proposal, but there have been many problems with finding a theory of everything over the years, as Einstein found out.
Right. In this particular case, from what I have read, the idea that space-time may be classical, that's their argument, and not quantum at all. That's one of the broad points that's been made. And then they get into rather complex calculations, which obviously are beyond my pale. I understood, but not quite. Do you think if that is the case, then what impact it might have on the concept of multiverse if this theory is solved?
Well, So there are many different types of multiverse models, as I discuss in my book, The Allure of the Multiverse. There are multiverse models based upon general relativity and extensions of general relativity. There are multiverse models based purely upon quantum physics and the idea of a Hilbert space.
Right.
So you have a Hilbert space, which is kind of an abstract space of all the quantum possibilities. And then you have real space time, the space time we experience, in terms of, uh, for example, that the sun is curving space time in Earth's vicinity and physically causing Earth to travel in an elliptical orbit rather than in a straight line. So that is a very physical, very tangible thing. And interestingly, since Einstein proposed a general theory of relativity in 1915, there have been no deviations. Every test of that theory has become uh, a proof that it's 100% accurate. So if that's the case, it could be the case that general relativity is something fundamental and that quantum theory has to be applied to other forces, but it could be that somehow gravitation is something very different. It's not the type of energy fields that quantum physics deals with, but is something just fundamental in geometry and something that must be considered separately. So that is certainly a possibility. But in terms of multiverse models, there is a very clear multiverse idea in the inflationary universe where you have solutions to general relativity in which space-time or space over time rapidly expands, and that can be triggered by a quantum event or some kind of energy field. But in essence, it's a classical theory based upon quantum energy fields, and that it's very, very easy to trigger it. And because of that, we imagine early space-time as possibly being something like a bubble bath with many different bubbles expanding at different rates. And one of those bubbles ended up being our universe. But it's very possible that there are other bubbles out there, other bubble universes that are now beyond our detection and beyond the observable universe. But it's possible that very early on in the universe, some of these bubbles collided with ours, and it is conceivable that we could even detect these collisions and prove that there are other universes out there, which is very exciting.
We have barely begun to figure out the one universe that exists and that we live in. What is propelling the wish to look for a multiverse?
Well, if we look at the parameters of our universe, such as gravitational constant, the fine structure parameter, which basically tells you the strength of electromagnetism, and the cosmological constant, which is something that was originally added on by Einstein as kind of an anti-gravity factor, but has turned up in two situations. One is that the universe is accelerating, and cosmological constant is a easy way to explain uh, that the why the universe is accelerating, although we don't really understand what drives that. Some people call that dark energy. Yet in standard quantum field theory, if you calculate all the energy fields in the universe and the net effect, that also yields a cosmological constant. And that cosmological constant is astronomically large, much, much larger than what is detected. So weirdly enough, there are two theories of the cosmological constant, and they're very different. And one idea for resolving that is to say, hey, wait a minute, our cosmological constant is unusually small. And if you could calculate the cosmological constants of an array of universes by comparing universes, that we would be an oddball, that we are a universe which happens to have a very tiny cosmological constant. But then out there are other universes, possibly with larger cosmological constants. But then, because of the anti gravity of those cosmological constants, they would have expanded so quickly that structure wouldn't have formed. There wouldn't be galaxies, there wouldn't be stars, there wouldn't be any living beings to talk about the fact that they're in that universe. And that's something called the anthropic principle. And one way of expressing the anthropic principle, which is the idea that our universe is the way it is because otherwise we wouldn't be here, is to imagine an array of parallel universes. So it's an elegant way of talking about why our universe has particular parameters. But at the same time, some physicists don't really like the idea because of the fact that we cannot directly detect these parallel universes. Wouldn't it be better to have a comprehensive theory of everything, a theory of our universe, why it has these constants, without invoking the anthropic principle, without invoking other universes? And I agree that if we could come up with a theory that only involves a single universe, that elegantly explains why our universe is the way it is, that would be much better than having to invoke the idea of other universes. On the other hand, if we never come up with a theory that's satisfying with a single universe without invoking the multiverse, isn't it better to have a multiverse and an explanation for our universe that is ironclad and explains everything than to have no explanation of our universe?
Let me ask the question that you yourself raise in the book. Why not just stick to the measurable and map out the recordable using powerful instruments such as the James Webb Space Telescope? Why not indeed?
Yeah, so well, we like to see pictures of things. There's an expression, a meme, picture it didn't happen. So we like to see visible evidence. So that's the exciting thing about the James Webb Space Telescope, is that we can see farther back in time than ever before, farther out in space, which is far back in time. So that is very exciting, and that's something that appeals to many people. And ideally, we'd be able to map out the whole physical universe, to be able to image the whole physical universe, and to come up with a satisfying theory of the universe based only upon this tangible physical evidence. But there's a big problem with that, and that is that only a sector of the universe is observable. If you go far enough out, then light will not have time to reach us farther out than a certain limit, something like 46 billion light years away. Beyond that limit, that is called the radius of the observable universe. We don't know what's out there. So the question is, should we just ignore that, or can we speculate about that? Another question is, and we certainly don't want to think that the observable universe is everything that's out there. That would be kind of odd if the only thing that's out there is everything we can see. But then to bring in quantum theory says that on a fundamental level, because of the Heisenberg uncertainty principle, we cannot measure everything all at once. So there is always going to be hidden alcoves, what we call Hilbert space in quantum mechanics, this idea of an infinite array of possibilities, and we can only detect a certain fraction of that, but there are always going to be things that we cannot detect. So we can't really say, as much as we would like to, that only things that are visible and directly detectable are valid. In some ways, we need to consider things that are only indirectly detectable.
But the JWST is seeing things, some of which have the potential to threaten the way we understand the universe. For instance, that galaxy, the ancient galaxy, which was formed barely 390 million years after the universe was supposed to have been born. And there is also the question of the Methuselah, the star, which is apparently older than our universe. How do we reconcile those observations with what we are talking now?
Well, that is a big question, and that's the exciting thing about the James Webb Space Telescope, is that it's revealing new facts. Galaxies that are much more developed than we expected for such early galaxies, baby galaxies. We're seeing things that look like uh, galaxies that are closer to our time. So the question is the universe older than we think? Are our models of galaxy formation wrong? Might there be a way that galaxies can form very, very quickly? That's another possibility. I read recently that we've seen large black holes very early on too, which were not believed to have occurred so early on. So this is a really exciting time for astrophysics and cosmology, and there may be some new theories of star formation, galaxy formation, and even new cosmological theories that emerge in the coming years. So it's an exciting time to go into those fields. If young people want to think about physics careers, I would strongly suggest astrophysics and cosmology.
Speaking of perhaps revising the age of the universe, you're probably aware of a recent paper by Professor Rajendra Gupta of University Ottawa, who, based on the JWST, calculated the age to be 27.6, I think, billion years, not 13.8 that we have lived with. And he also brings in things like the tired light and redshift and those ideas into it. I had an interview with him some time ago. Of course, according to Dr. Mather, whom I interviewed as well, he considered that to be a minority view, but it's an interesting idea that the universe could be older than what we think.
Yes, well, interestingly, for many years, including when I grew up, the age of the universe was very uncertain, and it was being revised almost constantly, and there was a great range. So it was something very inexact, and then I guess about 20 years ago, physicists developed what's called the concordance model of the universe, which said all the known data matches up to about 13.7 and later revised to 13.8 billion years. And that is a very powerful model. And there is a lot of data that suggest that the universe is 13.8 billion years old. But at the same time, some of this new evidence from the James Webb Space Telescope about galaxies, information, and so forth could very well point to a different age of the universe. But a lot of revision would have to be made, and that would have to be consistent with all known data. So, as far as I know, there are no models in which the universe is much older that are consistent with all known cosmological data.
Right. Again, I'm quoting you here between absolute realism demanding photographic proof or equivalent to support the existence of multiverse and the landscape of that embraces every conceivable option. Where do you come down?
Well, I'm open-minded, and I tend to be eclectic and interested in a range of theories, just because I like to think about all the possibilities, and I'm not wedded to one particular perspective. So my book tries to look at many different perspectives that fall within physical reality, that are physically realistic. But I have to say that I don't really believe in absolute realism at this point, because quantum theory tells us that you can't measure everything at once. Position and momentum, according to Heisenberg, cannot be measured precisely both at once. Uh, it's somewhat like an old-fashioned television set where you try to tune the vertical, you try to tune the horizontal, but you still get, if the vertical is clear, the horizontal is fuzzy. If the horizontal is clear, the vertical is fuzzy. So you can't get an absolutely picture perfect image of everything in the universe that also records velocity as well as position. So realism is out, and also you have these phenomena such as quantum entanglement, where something that happens in one part of space time can be correlated precisely with something that happens in another part of space time. The classic example being particles that have quantum spin. If you know that one of them has a spin up and there happen to be a quantum pair, the other has a spin down. So it's very strange. If you measure one, instantly the other one has a measurement in the other direction. It's not quite causality. It's a kind of long distance correlation. So that leads me to believe that local realism, which was the goal sought by Einstein, that you have determinism that is exactly transmitted from point to point. If you look at quantum phenomena, that's not true. On the other hand, do we want to go to the other extreme, which is like, for example, in string theory, talking about 10 to the 500th power possibilities and kind of treating them as all different parts of the same multiverse? Well, that gets almost a little bit you know abstract. It gets it's very strange to think, okay, we're just one of 10 to the 500th possibilities, and that somehow we can narrow all of those down perfectly to just the one universe we're in. So I guess that's a bit of the other extreme,
Right.
but I'm interested in finding the happy medium between both, where you have an exact depiction of the observable universe, but it's possible that that could include some unobservable elements.
Aren't you troubled that even while imagining a multiverse, we remain anthropocentric in the sense that we imagine what parallel us would be like? Why not remove us completely from a parallel or a multiverse situation? Why should we be there? Why should a new Mayank Chhaya in the next universe? It's conceivable that it's completely different, don't you
Yeah,
think?
and I'm being interviewed by that alternative reality of you right now as we speak. But but that was the question asked by Hugh Everett, um, who was a graduate student of John Wheeler, and he wondered, why introduce the human element? Why introduce observers into quantum physics to collapse the wave function to perform this task? Because the universe should be completely consistent without people. And since then, the idea of orthodox quantum physics, called the Copenhagen
Right.
interpretation, has been modified through the idea of decoherence and saying, well, maybe it's not the people itself who are causing the collapse, but maybe it's interactions with the environment in general that causes this degradation, which is a very interesting idea, that it's not exactly people, but our atoms are somehow interfering with processes, combining with atoms that are being measured to decohere them. But Everett came up with a very radical solution and said, well, okay, we see a precise value of certain measurements, but maybe in reality, that quantum state stays a mixture of lots of possibilities, and we are a mixture of lots of possibilities, and that each of these versions of us sees a different measurement. So we're kind of an array of quantum possibilities, and there's a complete consistency, and there's really no effect of the observer and no effect of people, and that we might as well not be here. But since we are here, we have to exist in a mixed quantum state, a superposition, but we have the illusion, each of us, each version has the illusion that they're the real person and never realizes that they're part of this array of possibilities.
So in a sense, in the observer observed dynamic, even the observer is a sort of collapsing wave function at
Well,
that point.
the observer's not collapsing, nothing collapses. The wave function remains intact, but the observer is bifurcating. Their consciousness splits into multiple possibilities. So, for example, if you're recording what happens to an electron spin when you turn on a magnet, and the two possibilities are the electron can be aligned with the magnet, which would be spin up, or counter align with the magnet, which would be spin down. And there's a 50-50 chance of either possibility. Well, The classical interpretation, or I should say the orthodox Copenhagen interpretation, is that the observation collapses the wave function down into either spin up or spin down. The Everett interpretation is that the observer has two possibilities. One is an observer that records an upspin, and the other is an observer that records a downspin, and they remain in a mesh or superposition of both possibilities and go on and live their lives. And both of them are convinced that they're the right version, the right person, but don't realize that they have a doppelganger or near doppelganger in the other parallel universe.
Right. This is perhaps an absurd idea, but I wanted to bounce it off you because I know you're an eclectic mind. What if, from the standpoint of quantum particles, we also, if quantum particles were looking at us the way we look at them while observing, when they look at us and when we look at us simultaneously, both the functions are collapsing, and therefore we can see each other. And then we move on to our fuzzy world in multiple states that we both are simultaneously when we are not looking at each other.
Well, that would be interesting because I guess there are some ideas, maybe minority ideas, that say, well, maybe consciousness, which is a great mystery, maybe consciousness is something that is shared by everything, and kind of a cosmic consciousness that's shared by all things, and that every particle has little bits of consciousness. I don't want to draw that conclusion because I frankly I don't really understand where consciousness comes from. It's strange to be able to have the feeling that I'm self-aware and that I have free will and that I can make a decision, and based on that decision, things happen. It's a very strange thing, and I'm not sure if anyone in science has been able to fully explain consciousness and free will.
Right.
But what that would be interesting if particles were able to somehow detect or observe people. I mean, I guess more realistically, they are entangled with the quantum states of all the particles in people. So it's
Right.
just the kind of entanglement that a mutual entanglement that might cause through decoherence a kind of a distillation from a complex state down to a simpler state.
Right. Do you believe that if the universe, if a multiverse does exist, the same laws of physics would apply? And the reason I'm asking is why could one of the universes have the speed of light as the ultimate lock on things for transmission? There could be a universe where the speed of light is not the ultimate speed like we have here. Is it conceivable, or we are so trapped in looking at everything from a human standpoint that we cannot imagine anything else?
Yes, well, the MIT physicist Max Tegmark proposed multiverse, a complex multiverse, and one of the possibilities was that there are universes with different mathematical laws, which is kind of mind-blowing. I guess I'm a little more conservative in the sense that I just imagine, as going back to the idea of a bubble bath, that in the process of inflation, all these bubbles arose, and they could possibly have some different parameters. I'm not sure if the speed of light could be different in some of those. That seems very fundamental, and no one has ever found any deviation from the speed of light. But more mysterious is this cosmological constant. And since you can derive the cosmological constant from first principles using quantum theory, it's possible that you have different cosmological constants in different universes. Other parameters, other factors like the strength of electromagnetism, it's conceivable that could differ in different universes.
Right. You point out in the book that the term multiverse did not originate in physics. It was
Yeah,
the American philosopher and psychologist who introduced it in the 1890s as a way to describe, as you say, morally ambiguous cosmos. Talk a bit about that.
Well, that was a William James, who
Right.
was considered one of the founders of psychology, a philosopher, and he was talking about um, the idea of moral ambiguity, and he coined the term multiverse to kind of describe the idea that the universe is really not one thing, but contains both good and bad, both positive and negative things, both evil and beneficial things. And he was trying to say that we should accept a mixture, a little bit like the idea of in Taoism of yin yang, this idea of you have darkness and light in a mixture, and that you have good and bad, and a lot of Eastern religions in particular have this idea that you have a constant mixture, a churning of creative and destructive forces, and that the universe is constantly recycling. Some of the ancient Greeks, such as Empedocles, talked about that the universe is going from positive to negative, and that everything is kind of a mixture of things. And I think that's what William James was getting at in talking about the multiverse, saying that it's kind of a mixture, an ever-changing, uh, churning mixture of substances, not a single entity.
Yeah. This is again speculating a bit. Imagine, if you will, that there is the universe being what I call situationally stochastic, in the sense there are situations where laws of physics break down, otherwise they generally work. Uh, it, do you think that's possible, that something like that can exist? That it is situational, but otherwise everything else is the way we imagine it to be.
Well, we see that a lot in physics. For example, in thermodynamics, we have certain rules for, if you add a certain amount of heat to raise the temperature of something, but then you have phenomena such as supercooling at very low temperatures, where the standard laws of thermodynamics and organization seem to break down. You have superconductivity, where Ohm's law, which says that voltage and current are proportional to each other. You see, most materials such as metals and at ordinary temperatures, if you want to push electrons through a wire, you crank up the voltage, and the more you crank up the voltage, the more current you get, and that is a very simple law. But then you get to superconductors, and those laws break down. So it's entirely possible that in different regimes, known laws, things that we consider very familiar, break down, and things go a little bit strange, a little bit
Right.
wonky.
Are laws of nature slash physics a consequence of the universe, or the universe is a consequence of the laws of nature and physics?
Well, that is a very deep question, whether or not the laws came first, or the laws developed very early on in the universe. That was something that one of my heroes, the physicist John Wheeler, was constantly trying to decide and come up with. He spent most of his life trying to develop, what is the most fundamental thing. And that's where this idea of superspace came up. He came up with that idea that maybe the universe starts in a mixture of geometries, a mixture of laws, and almost this amorphous foam, which you call quantum foam or space-time foam, and that somehow things got distilled into more regular laws over time. And so he came up with different hypotheses for that. In his later years, he imagined almost that consciousness, that by looking back in time, that our free will helps distill the early universe, which is a very strange idea. He called that the participatory universe, that by looking at the universe, we actually change it, and that we change it in a way that produces us, which is a very weird idea.
Right.
I had the pleasure of interviewing him before he passed away, and he was talking about some of his deep questions. wondering what the relationship is between consciousness and the universe. But it is entirely possible that in the very instance of creation or the Big Bang, that certain laws were altered. Some physicists think that all the forces of nature were the same strength and even possibly the same carrier, the same particle very early on, which is the idea of either grand unification or theory of everything. So that's entirely possible that things were either in some ways more uniform because you could have very simple laws, or in some ways could have started out completely turbulent and led to some such unification uh, in the fledgling instance of the universe.
Right. What do you think of Roger Penrose's conformal cyclic cosmology, which you refer to in your book as well? And by his own description, these are his exact words. He says it is a bit like Hindu philosophy. That's his. I'm quoting him verbatim. Now, growing up in India, the idea that the universe is infinite and it just generates and regenerates was almost a given uh, for me and when I was growing up. So when I read Penrose's conformal cyclic cosmology, I was quite fascinated by that. What do you think?
Well, Hinduism is really interesting in terms of talking about the endless cycles of creation and destruction, and the idea of Shiva, part of the uh,
Right.
part of the Trinity of gods, and talking about Shiva's uh, efforts to recreate the universe, and that creation and destruction are two sides of the same thing, and that the universe goes through cycles, that there are kalpas and mahayugas and yugas, and these are all cycles of various lengths of billions of years, thousands of years. That is fascinating, and that it appeared so early on in the history of the world in ancient Hinduism. I find that very fascinating. So I can see why Roger Penrose is drawing an analogy there. Um, Not that I'm an expert in theology by any means,
No, I understand exactly. Well, you got it absolutely right.
but that's very interesting to me, and
Yeah.
that other physicists have been interested in that over the years,
Right.
such as Schrodinger and so forth. Um, but you know, a lot of people philosophically feel more comfortable with the idea of cycles, and Penrose's idea wraps everything up, and you don't have to talk about the universe popping out of nothing, and
Yeah.
that's the strange thing. The idea of a big bang and having nothing before it is really odd.
Right.
And very early on in the history of cosmology, a physicist, Caltech physicist Richard Tolman, talked about the oscillating universe, and that the universe goes through cycles. But the big problem was that entropy or disorder is built up in every cycle. So every cycle doesn't start out afresh. It starts out with waste energy, waste material.
Right.
So the universe gets more and more of this waste material until eventually it just kind of flags out, just, you know, uh, ends up no longer cycling, which is very unsatisfying if you believe in endless cycles. So Penrose came up with an idea of resetting entropy by equating entropy with part of the tensor, which is a technical term for the mathematical structures of general relativity, and saying, well, part of this mathematical entity is connected with entropy, and we reset it to zero at every cycle. So the entropy is reset, and then everything starts afresh, which is in some ways very satisfying. And Penrose is a brilliant thinker. I had the pleasure of talking to him when he gave a talk some years ago, and he's a very creative and very kind individual. And it is a very exciting idea, but it is very mathematically abstract.
It is.
And some people, he tried to identify proof in the cosmic microwave background of these particular kinds of circles that in the background, but no one has really found evidence of earlier cycles. So
Right.
they've looked for it, But if we did find evidence of earlier cycles, that would be very, very exciting.
Just last couple of things, Professor. One is a universe this vast and unfathomably complex. Why can't it have, as it were, two distinct and compatible operating systems? Why look for a unified explanation of everything? After all, it is a remarkable system, right?
Yes, that is very interesting because quantum electrodynamics and its extension, which is the electroweak theory and the standard model, are really perfect theories in terms of prediction. You can predict electron scattering perfectly. You can predict radioactive decay perfectly. It's really amazing. And then on the other hand, you have general relativity, which is perfectly predictive of how planets move. It's predictive of black holes and so forth. So we have these two theories, and why not rest and say, okay, we have these two theories. They're very different and they apply on different levels, and we're satisfied there. And the main problem with that is that when we talk about things like black holes, and we talk about things which are at the intersection of gravity and quantum phenomena, then we come up short, and we don't really have a good theory of what happens to particles at when they are in intense gravitational fields.
Yeah,
So that would require some way of finding connections between the two theories.
right.
So that would be a reason to tie the theories together. But it might be that there's just some kind of hybrid that perfectly respects general relativity and perfectly respects quantum theory and just applies to these very intense, high gravitational, high energy situations.
Yeah, but there is already an equilibrium between the quantum world and the macro world without us trying. It neither is disturbing the other in any significant way, from the looks of it.
Yes, well, there's an expression, not quite sure who coined it. It's kind of a cliche. Don't worry about quantum physics, to shut up and calculate, and that
Yes.
everything will turn out to be okay. And I think that expression's been attributed to different physicists, but I think even Richard Feynman, who was very practical and pragmatic, engaged in philosophical speculation, although he didn't like to admit it. One point, he went to a philosophy of time conference and went by the name Mr. X because he didn't want to be quoted as being too speculative because
I
he didn't
see.
like philosophy. But practically every physicist who, once they make a name for themselves, is asked to speculate. And Einstein speculated, and we started out as very pragmatic and ended up being very speculative.
Yeah. To conclude, Professor, I want to take you back to some 15 years ago at a Stanford panel where you were one of the panelists. Uh, you were asked how seriously you took the multiverse concept. The options being would bet your goldfish, your dog, or your life. And you said you were nearly at the level of betting your dog. Does that still remain the case? Because as you again point out, Steven Weinberg had a very interesting joke about it. He said, I would bet Martin Rees's dog and Andre Lynn's life.
Well, not to correct you, but I was not part of that Stanford panel.
Oh, I see. I see.
But
Okay. I'm sorry about I think I misunderstood.
I mentioned that in my book. Uh,
Right.
that I think that was involving that was a story told by Martin Rees about
Okay.
about an interaction with Andre Linde.
Yeah.
But that's a very interesting story and very amusing story. But personally, I would not bet anything personally on the
Oh,
multiverse at
oh
this
really? Okay.
point. But I don't bet.
That's
but
true.
but I love the bets of physicists such as Kip Thorne and Stephen Hawking, and all of them have made wagers
Yeah.
uh, on various topics.
Right.